This is our Chapter 5, Lesson 1 homework video on randomness, probability, and simulation. And our guiding question here is, what does probability of a specific outcome mean in terms of the law of large numbers for the short term and the long term? Or to say it more generally, what does a probability tell us? Does it dictate an outcome, or does it tell us a likely prediction? Does it give us an estimate or an exact number? So we're going to represent a probability as an event where the numbers between 0 and 1, or 0% and 100%, in terms of 0 being no chance of occurring and 100% being always occurring. Now the key to a lot of what we study this year and to probability is the law of large numbers. And that's what probability is really telling us, is that it's telling us what are the proportion that our outcome will approach as we extend the number of trials. So as we extend the number of times we roll the dice, the proportion of times that we would expect to get snake eyes or 2 sixes. So it doesn't dictate single outcomes. It does not dictate even 100 outcomes. It just helps us understand what proportion a series of outcomes should approach in a large number of trials. So law of large numbers, as the number of trials increases, our number of successes should approach the probability, will likely approach the probability. Over a small number of trials, the proportion by chance may be very far away. However, as that number increases, it's more and more likely to approach the actual probability. Now, myths here are that it dictates outcomes. That if, oh my God, you're playing roulette and the wheel spun and it got red 5 times, it's got to be black next time. Or this hitter is a 300 hitter, meaning 3 out of 10 times at bat he gets a hit, and he's 0 for 7, so he's going to get 3 hits the next 3 at bats. That's not what it tells you at all. So we have to get this idea that probability is not dictating outcomes. It's telling us the likely number of proportions of successes over a large number of trials. So as the number of trials n increases, the proportion of times the event occurs approaches that probability, should approach, tends to approach that probability. We're often going to perform simulations in order to estimate a probability. For some outcomes this is required because we don't have a way to systematically calculate the probability. Rolling the dice, if we know that each side, there's 6 sides and each one has an equal chance of occurring, it's a 1 in 6 chance. However, with other things in real life, we don't know, we may not have a way to quantify it, so what we need to do is have a series of simulations in order to estimate the probability. To do that, we're going to follow the same plan: state, plan, do, conclude. State the question of interest, what are we trying to estimate, which chance process, and define the variable. X equals the number of times we'll roll a 6 with 1 dice, or the number of times we'll roll 3 5s when rolling 3 dice, or the proportion of times. If we're stating the number of times, we stated a number out of a number of trials. If we're stating a proportion, then it could apply to a variety of number of trials. We will plan by saying how to use, what process we're going to use, what outcomes satisfy it, and what our sample space is, which we're about to talk about. We're going to describe in depth how to go through one repetition of the process, so somebody else trying to repeat our process could do the same. We're going to perform many repetitions of the simulation. Again, the law of large numbers. The more times we perform the simulation, it's likely that we're improving our estimate. Conclude, then we're going to interpret our results to answer the question we stated. Now, with a simulation, keep in mind that probability is not dictating outcomes. So the more times we do, so if we roll the dice 100 times and then get a proportion of times we got snake eyes, and then we roll it another 100 times in the proportion, another 100 times, each of those could be different proportions. The more times we do it, if we averaged all those, then we would tend to get a value closer to the true probability. That doesn't mean we're going to get that every time we have 100 rolls of the die. By chance, we might have a different proportion each time. Now, if we can determine an outcome isn't plausible, that doesn't mean a process isn't fair. So oftentimes we'll try to repeat a process to say, oh, could this have really occurred the number of times this person is stating? Just because we perform one simulation and our number is not close to a claim does not mean the claim is not true. We'd have to have a very large sample size. We'd have to quantify that by having repetitions in order to see that something is not plausible. So the idea of probability is really key to 5.1, where we look at the intro to probability, that it doesn't dictate outcomes, it just gives us an estimate that are a proportion that our chance outcome should approach in the long term as we increase the number of trials. Let's look at how we define probability in different ways we look at probability models. Two key things: probability rules, and then a common confusion is mutually exclusive events and independent events. We talked about this at the beginning of the year. Independent events, we don't call variables independent, as you may have in prior math classes, because independence means the outcome of one chance process does not affect the outcome of another. So the outcome of one variable does not have any effect on the other. Meaning, if I roll a 5, that has no bearing on whether I'm going to roll a 5 in the next process, in the next roll. Now, if my outcome is rolling a 10 for the sum of 2 die rolls, rolling a 5 on the first roll does have a change on the probability of getting 10 in the first 2 rolls of the die. So independence means the probability of one outcome affecting the probability of another. If two events are independent, then if one occurs and the probability of a second event is unchanged, then those two events are independent. However, if a first event occurs and the probability of a second event changes, then those are not independent. The difference here, mutually exclusive events, both cannot occur. So an example would be rolling a 1 and rolling a 2. On one roll of the die with one die, I cannot roll a 1 and a 2. I can either roll a 1 or a 2. So the probability of rolling a 1 goes to 0 if I'm given the fact that I've rolled a 2. That means that they're not independent. One occurring changes the other. So mutually exclusive events can never both occur. And because they can never both occur, they are not independent. So mutually exclusive events are never independent, and that's a key thing to look over for this chapter. Now let's look at a sample space, which means all possible outcomes of a chance process. Here we're looking at all possible outcomes of rolling 2 dice. So a sample space represents all possible outcomes of a chance process. Because there are 6 possible outcomes for the first die and 6 for the second, 6 times 6 being 36. So there's 36 combinations or possible outcomes when rolling 2 dice. Here are all the possibilities if you roll a 1 on the first die. The second row represents all the possibilities if you roll a 2 on the first die. Over here are all 6s. It got a little blurry in my picture. So a sample space, this is all possible outcomes. 36 possible outcomes of rolling 2 dice. Note that that gives us our denominator for all possible outcomes. So we'd count up the number of outcomes that satisfy whatever we're interested in. For example, rolling a 3. So we'd count up the number of these outcomes that add up to 3, and then divide that by 36, the total number of possible outcomes, to determine the probability. Let's see, what adds up to 3? A 1, 2 adds up to 3, and a 2, 1. So that's 2 outcomes out of 36. So the chance of rolling 2 dice and having a sum of 3 on the 2 dice is 1 out of 18. You could also represent that as 2 out of 36. Since in probability, it's informative to not reduce the fraction, because the numerator tells us the total number of outcomes that satisfy the chance process, and the denominator tells us the total number of possible outcomes. So it's totally correct if you left that probability as 2 out of 36. So we'll call our sample space S for chance process. This is a probability model describing a chance process. So that it consists of a sample space S, all possible outcomes is what that entails, and then a probability for each outcome. So for a coin flip, much simpler. Our sample space for one coin flip is heads, tails. We'd represent that as this, an S, and then these squiggly parentheses, H, comma, T, where H is heads and T is tails. There's 2 outcomes, so the probability of heads is the same as the probability of tails. They both happen 1 out of 2 possible outcomes, or 0.5, 50% of the time. For a roll of the die, of one die, our sample space would be represented as you've seen down here, where the possible outcomes are all listed in there. 6 outcomes, with each having a probability of 1/6. An event is any collection of outcomes from some chance process. I just mentioned the event of the sum of the two dice being 3. That would be an event. It's a subset of the sample space, meaning some combination of the outcomes from the sample space. Usually we'll talk about these events as event A, B, C, D, if we want to indicate different types of events. So what I'd like you to do right now is consider flipping 2 coins. We just talked about 1 coin. And event A being flipping heads on the first coin, while event B is flipping heads on the second coin. Define the sample space for flipping 2 coins, and then describe whether events A and B are mutually exclusive or independent. And pause now and answer the multiple choice. Let's go through some basic probability rules. So for any event, the probability is always between 0 and 1. If S is a sample space in probability model, it represents 100% of the outcomes. So our sample space, it represented all outcomes. So the probability of one of those outcomes occurring is 100% because they're all included. We determine the probability by the number of outcomes that correspond to a success of NA, like rolling 2 dice that sum to 3 out of the total number of outcomes possible. Here's our example of rolling a 3. The probability that event A does not occur is called the complement of A. So the probability that we don't roll a 3 would be 1 minus 2 out of 36, or 34 out of 36. The 34 outcomes that involve us not rolling 2 dice that sum to 3. If 2 events have no outcomes in common, that's represented in the Venn diagram here. There's no intersection where both A and B occur. These events are mutually exclusive. That means if A occurs, B is not occurring. So they're not independent. If A occurs, there's no possibility of B occurring. If events A and B are mutually exclusive, the probability of either of them happening, you just add them up. Here's a nice visual for the complement. The probability of an event and its complement always equals 1, because it's probably the event happens and that it doesn't happen. That has to always add to 1. Okay, Venn diagrams get a little complicated for some students, but they're a nice way to visualize a process. The whole rectangle represents all possible outcomes, so 100% of outcomes are in our sample space there. One event is represented by a circle on the left, the second event by a circle on the right. Note that right here this indicates that these events are not mutually exclusive, because right here they both occur. Now, when we sum up the sample space, all of this inside here equals 100%. One interesting thing is now if these events have an intersection, that's right here. That means they both occur. Just like the intersection of 2 streets is where both streets you're on both streets. When you're on the intersection of Ellis and Goff, you're on both streets. So the intersection of 2 events is when they both occur. The union of 2 events is when either occur. So either you're on Ellis or Goff Street. So there's a much larger probability to be on either because that involves just one or the other happening. Note that if we added up circle A here, if we added up circle A and circle B here, we'd be counting this area in the circle twice. So when we add up the probability of A or B and they have an intersection, what we have to do is add circle A and then add circle B, but because this part was included in both of those, then we subtract it from the 2. So the probability of A or B occurring is the sum of the 2 circles. However, both events occur here, so we've counted that twice. So when the 2 events have an intersection, we have to add the probability A plus the probability of B and subtract their intersection. This represents their intersection in green here. So we note this with this notation with the little n. That means that A and B occur. The union, or either occurring, is represented in green down here. So either A or B, or both happen. And we represent that with a U. U for union, N, or an N looking thing for intersection. The U for union means the probability of A or B occurring. So we call this the union of the events. Again, the union of the events would equal probability of A plus the probability of B, and we'd subtract that intersection, the probability that either happens, because that's included in both probability of A and B. So it gets counted twice, so we subtract it once to find the probability of either happening if they have an intersection. And that leads us to here. G here is the same way of saying the general addition rule for 2 events. So that's probability of A or B occurring. We add up probability of the first event plus the second and subtract their intersection. If they're independent, then their intersection will just be found by multiplying the 2. So if one happens 10% of the time, the other happens 50% of the time, this value would be 0.05. 0.1 times 0.5 or 0.05. All right, in honor of our World Series champion Giants, here is a question about probability and the Giants. So throughout the course of his World Series games, that's 3 World Series, 2010, 2012, and 2014 that we just won, Pablo Sandoval has 20 hits and 47 at-bats, giving him a batting average of .426 or .426. So that is like a simulation of his the probability of him getting a hit. If he were to appear in 3 more World Series and have an additional 47 at-bats, does this mean that he would have exactly 20 hits? Why or why not? Please pause now and answer the free response question after you've gone over the summary for 5.1 and 5.2 and looked over vocab and examples.